Okay, so so far we only talked about graph-based slang with the so-called post graphs. So where every node in the graph corresponds to the position of the robot. We haven't had any other types of nodes. This will change today when we look into landmark-based slang. So we have landmark observations that we observe. So far, with only nodes and an edge is a transformation between two nodes extracted from this what we call virtual observations. And today we're going to leave that behind or come up to a graph representation where a node can be either a position of the robot or a feature in the environment that we can observe. Okay, so far the vertices or nodes in the graph were x, y, theta locations and relative transformations among them. And today the question is how to deal with landmarks. So if we deal with landmarks, so in a visualization here we have kind of features or landmark locations, and we have our robot which moves through the environment, and the robot can observe those landmarks. This is typically a relative observation. You can see that as a range bearing observation. This can be kind of a virtual sensor which measures delta x, delta y if you want to. You can also have range information only, depending on your sensor, just provides you range information only, bearing information, which is an example for visual sensors, where you only know the angle in which you observe the feature, you see in your camera image, but you don't have you have no information about how far it is away, because a single camera image doesn't provide the depth information. So different kind of observations you may obtain, and you may want to represent to actually build up this graph, this robot positions and features. And so we will look today into what changes if we have this kind of representation, or what do we need to change in our optimization framework to deal with these situations. So there are a couple of real-world environments, like here this Victoria Park data set that we've seen a few times during that course, where the landmarks are the trunks of the trees in the environment, and the robot moves through the environment, observes here, whereas it scanners the environment, extracts the trunk of the trees, and uses every tree as a landmark or as a feature. So we can also visualize this. So if the post graph is only in this graph over here, we now have features indicated by these stars, and this is a feature observation or landmark in the environment. And now we also want to estimate the position of those features. The problem we typically have in here, one of the problems that we'll encounter during the course today, is that depending on the information my sensor provides me, I may not be able to actually estimate the location. So, for example, if I have just a single camera, so a bearing only observation, I observe a feature only once, so only from the same position multiple times. I have typically no means for reconstructing the position of that feature. I only know it lies somewhere on a line in space because I just know the orientation given my current pose, but I don't know where it is. If I see that feature from a different position in the environment, I may be able to estimate where the feature is by a kind of triangulation. So if I've seen the feature in this direction, then traveling over there and seeing it in this direction, by kind of triangulation, I may be able to identify where that feature is. So it may be the case that the problem with those landmarks, depending on the sensor observation I get, I may not be able to actually estimate the position of some of those landmarks uniquely in the environment. Okay, so what changed so far? If I have my graph with landmarks, the poses, we have kind of two types of nodes now in this graph. The one can be the robot's poses, the other one can represent those landmarks. And the edges are typically now only odometry information. That's the information which connects those nodes here incrementally. And we have just landmark observations, so robot observing a landmark from different positions in the environment. What we typically don't have here is kind of these virtual information, virtual observations that we used so far, which relates to poses with each other. That's something I typically don't have in this representation. So just have observation of features, and based on mutually seen features, so seeing a feature from this location, seeing a feature from this location, I also may get to know something about the relative transformation between those nodes, or the relative information between those nodes. And so my state space is now bigger than before because the state space contains all the position where the robot was plus the location of all landmarks in the environment. So my state space is now bigger, and the output of the optimization should be the position of the robot as well as the positions of all landmarks. It's kind of clear what the difference between those, the post graph and this kind of graph these landmarks is. Okay, good. Okay, so let's start with simple example. We have an observation is a point in space on XY position. I don't know anything about the orientation of that feature, so it can be just a pole or a trunk of a tree or something like that. And I have a relative observation. Let's say, in the most easiest case, of a sensor where I can actually measure delta x, delta y, so delta x, delta y location to that feature. Okay, so the first thing I need to know, I need to compute my expected observation. Right, for coming up with my error function, I need the expected observation. And so in this case, the robots, so the odometry stays exactly the same as we had it before. Now it gets interesting when we have a robot and a landmark, so xi at the robot's post, xj is landmark. So I can represent that by it's the xy position of the feature minus the translation of the robot, and then the transposed or inverted rotation matrix corresponding to the robot's orientation. And if I then formulate my error function, let's say the most simplistic error function is just subtracting the expected measurement from the obtained measurement. So it's my expected observation minus the obtained observation, just look to the difference in those observations. Then this over here is my expected observation, what we had before, minus the observation I obtained. This is kind of the standard case if I have this delta x, delta y sensor device. Is it kind of, so is there any question about that? Yes, please.
Is it in robot's coordinate frame then, this error function?
So the error function is really just the difference between the observations. So the expected observation, it's kind of true. It estimates where, if the robot would sit in the node xj, where would it see xi? And this is in the robot's reference frame. So the virtual observation is in the robot reference frame, but only for the reason, since the real observation is also in the robot's reference frame. And so I need to compare both of them, so they need to be in the same frame. But it's kind of right, so this is a transformation from one frame to the other frame. Any further question? Okay. So how would that function then, the expected observation function, change if we look to the bearing only case? So where we only can measure the angle to the landmark, but we cannot measure the xy location as we did so far. So how would that look like? Small plot. So let's say this is my xi, where the robot is sitting, it's looking in this direction. And I have a landmark which, let's see, sits over here, xj, so this is my landmark. And the only thing that my sensor provides me is here this theta. Theta is not a good variable, let's call it whatever. Alpha. This is kind of the angle in which I measure my feature. So the robot looks in this direction and says, okay, I see a feature approximately whatever 70 degrees to my right hand side. Okay. So that's what I want to come up with. So if the robot would be in this configuration, how would the expected observation look like? how does that head look like in this case?
The rotation multiplied with translation because we don't have xj anymore.
So you can actually do it. So
It's our rotation matrix transpose multiplied by xj minus ti. So we don't have xj
times.
times the xj minus ti. Since we don't have xj, we omitted them. The rotation matrix multiplied translation.
But this would now be exactly the case for the xy. So what
We
will
don't
come
have
out
xj.
in here, what will come out here is a 2D vector. So this is a 2D delta x, delta y vector in space. But I need to end up in the space of orientations.
If we go with his suggestion, keep it there, we would just take the arctan of that result. So you have arctan of delta y, delta 2. And then subtract the global orientation of the robot. So
But we don't have this delta y and delta x anyway.
Let's do it that way. Just take the x j minus ti xj minus ti and take here the y coordinate and the x coordinate. So this is just the angle in the global reference frame. So this is my reference frame. It is gives me this angle over here. And then this is the orientation. Just have to should be.
it's like
So this is negative. First I go in this case to the negative direction. I need to subtract that. So what was that? The orientation of the robot. So it's just because in this term is negative here, so it won't be because we're going here. So if the landmark location would be here, you could better see that I need to subtract that. Okay. That's exactly what it looks like. So I have the robot on the landmark, and I compute. The first thing I need to compute is the angle between the post of the robot and the landmark, and then I need to subtract the orientation of the robot because I measure the orientation, the angle to the landmark given the orientation of the robot because the sensor is kind of mounted on the robot. Okay, so how does the error function look like for that? So this is my expected observation.
just subtract the
Exactly. So you just subtract the observation of J you obtained here. Actually, IJ there. So just subtract. This is what you expect. You just subtract what you get. Just look to the difference. So you want to minimize kind of the angular error between what you expect to observe and what you observe in reality. Okay, so that's kind of easy going. We can actually take those and then proceed with our error function. We derive our error function into the overall procedure that we did so far. In theory, we can do that, but we actually, turns out if we do that, we run into problems. And this problem can be partly observed if we look into the rank of this matrix H for ij. So what is the rank of this matrix Hij for a 2D landmark whose constraint? So if I have this 2D xy observation.
obviously it's rank 1 because we have 2D data, so we're missing one information on the we don't know the distance, right? So that's
No. So this is the first case where we have the delta x, delta y observation. It's not the bearing only case. We'll come to that in a second. I just said the first example where I can measure delta x, delta y. The second one would be, so this for the delta x, delta y. Yeah, haven't been explicit about that, sorry. What about for the delta x, delta y case? What's the rank of that matrix 2? Exactly, it's 2. The reason for that is, if you look to the Jacobians you have, the Jacobians are 2 divided by 3 matrices. You multiply Jacobian with Jacobian transpose, and but the rank of the Jacobian transpose times the Jacobian is the rank of the original matrix, the Jacobian, and it can only have rank 2. How is that different for the bearing-only case, for bearing-only constraint? So what do I measure?
And on the angle?
I measure only the angle exactly, and
So the rank is 1.
the rank should be 1 exactly. Because just get the information about the angle, I don't get the information about the position. And again, if you look to the Jacobian, Jacobian is a 1 by 3 matrix, a 1 by 3 matrix. Unless it's 0, has a rank of 1. Okay, you can also illustrate that by the question, we have the robot. So, say this is a landmark in space, and I have the situation where I have this delta x, delta y center. Where can the robot be? Same for range bearing. You can just form into delta x, delta y. Where can the robot be? If the robot observes a single observation of that landmark, where can the robot be? Sorry?
Back project.
I have not just understood.
No, sorry. It can only be on a circle around.
Exactly. It can be on a circle around. So if you see, the robot says, the landmark is exactly in front of me, 3 meters in front of me. If my notebook is not my landmark, I can be anywhere on that circle. The only constraint is that I have to be looking to my notebook. Exactly. So the robot can be sitting anywhere on that circle. Just the orientation is constrained. So it's a problem if I observe a landmark from one position, and I know where the landmark is, if for example, I cannot recover the pose of the robot completely. How does it look like? So the solution I get is kind of a 1D solution in space. So it's somewhere on that circle. How does this change if we have if I have a bearing only observation, so I just know the angle.
Yeah, everywhere can.
So the robot can be everywhere in the space, but the orientation is again constrained in a way that you should always see the landmark in a certain angle. So if now the camera here is my feature I observe, just know I observe in this direction, I can move away from the landmark because I don't know anything about the distance, or I can here move on a circle and again change the distance. So I can be anywhere in the xy space, I'm only constrained the observation. So it's have a 2D solution space in here. Okay. So what does that mean? So in the case where I work with landmarks and I build up my big H matrix by summing up these small matrices, I may end up in a situation where the rank is of this matrix, the H has no full rank. For example, if I observe a landmark, if this bearing only case I observe a landmark only once, there's no way for me to determine a unique solution for that system. So as a result of that, I don't have, or I can only obtain a unique solution if H has full rank. But if H doesn't have full rank, I can't obtain a unique solution. And the problem is, if I then want to solve my linear system, my Cholesky factorization, or whatever I do, the system will complain as the determinant is not the dimensionality of this matrix. So that's a problem. So if I have, let's say, I have n poses of the robot. N poses and n landmarks. So this is kind of 3D, x, y, theta, and 2D. How many observations are needed to either resolve the robot's pose or to estimate the whole thing at minimum, sorry, at least. Just at least needed.
2n plus 3.
So I have 3n plus 2m unknowns. Dimensional equal matrix, H matrix, and every small matrix gives me either 2 or rank of 2 or rank of 1. So I need at most 3n plus 2m or 3n plus 2m divided by 2 constraints. At absolute minimum. Typically, I would need more. I may observe one landmark 3, 4, 5, 6, 7 times, another landmark only once. So that's really a problem I have in here, that I cannot simply apply the standard solution to do it. However, there are means for dealing with these underdetermined systems. And one way to do that is actually to introduce a so-called damping factor in my linear system and not solve h delta x equals minus b, but solve a different system, which is h plus lambda times the identity delta x minus b. So I simply add, typically this lambda here should be small, should small value. So I add an identity matrix multiplied with a very small value. Why am I doing that? What's the result of that?
Adding some noise here, maybe.
You're not adding noise.
So
You're obtaining full rank matrix.
So exactly. So I obtain a full rank matrix if I do that, so I can solve that system. And what does this? What's the effect of that?
We'll get the unique solution.
We get a unique solution. That's right. And however, so the problem is that if I modify this matrix, I've changed my problem.
Yeah, but when the lambda is small, you change it really quite small.
That's absolutely right. But even if I change it a little bit, how do I change this? How does this change modify the solution I get, in the sense of in which way is the solution different?
referring to this hierarchical solution we just discussed.
Now, consider the example where you have H which has full rank. So you could solve the system without this factor and with this factor. What would be the difference in the solution if you may have this damping factor in there?
Kind of systematic error would introduce, which we then can reconstruct and obtain the real solution.
So if you consider the error I made last week, where I said we add this matrix which has a 1 in the first dimension, which means that I set delta x to 0. If I now add an identity matrix, it means I try to,
Maybe you pick a little more certain.
what I try to do, I try to add a constraint which try to keep the solution in its current position with the scaling factor. So this means I kind of say, don't change too much. I add a certain constraint. The smaller lambda is the smaller the influence of this constraint. That keep the system in its location. And then by combining those, I hope to find a valid solution for the old system. So it leads to the situation where kind of the additional constraint tries to, is one constraint that says the increments should be 0, should be small. That's kind of what this thing does. And the other one says, fit them I know to the solution I get, and the other one, let's say, you can see that, for example, if I have a bearing observation of one single feature, you say, the feature should be in this angle compared to my current location. I don't know anything about where it is in this direction. It seems just keep the landmark where it is in this dimension, just optimize this dimension. speaking in a very intuitive way. So about those dimensions where you can't infer anything, you say, keep the initial solution you have and just try to fix the rest. Just very, very informally speaking. And what happens if the lambda factor is much, much bigger than the determinant of this h?
Well, let's say the lambda factor happens to be 1, which is large in this case. Then we get a solution where essentially lambda times delta x equals minus b.
Which means?
Means delta x equals minus b. Because lambda is 1. So basically,
so what happens in the end that you get a solution which may be very far away from your original solution. So because the lambda identity may dominate this thing, the problem you solve. Because you're kind of moving away from your original problem. And this ends up in something which is known as the Levenberg-Marquardt algorithm, which you can use for solving such systems. So it's actually very similar to the, or it's a very simplified form of the Levenberg-Marquardt algorithm, which is very similar to the Gauss-Newton algorithm we had so far, except that we change the form of that linear system by adding this lambda times the identity term, and then actually vary that one. So I start with an initial lambda. I build my linear system in exactly the same way that I did before. I store the current error I have. Then I solve my sparse system. But now the sparse system has this lambda times identity term in here. I update my system and I check if the error has been reduced after the solution. If this is not the case, it's likely that I screwed something up, so I kind of back up my original system and I increase my lambda factor. So simply did some change which leaded to an error configuration which is higher than the error configuration I had before, so something I really don't want. So I end up somewhere in my space that I introduced a bigger error. And then I kind of recover my old state, so I kind of make a backup or restore my graph, which I back up before over here, and increase my lambda factor and then continue. If this is not the case, if the error gets smaller, I kind of can make my lambda smaller again to try to go closer to my original solution. And then I have a convergence criterion and a board. So this is one way for dealing with systems where H has not full rank. I try to do as good as I can to come up with a solution. Are there any questions about that? So in the end, the idea is very similar to the Gauss-Newton algorithm. The only thing is that I have this additional lambda times I, and I kind of vary my lambda space.
In the last line, it's just a typo, right? Lambda times divided?
Yes. Yes. So this should be equal to it. So it just
not the vector or anything.
No. Sorry. So this is really a typo. It should be lambda is half of its root value before. So kind of make it smaller. So things I kind of try to modify my problem. I say don't move too much. It's one part, and solve what you can solve, and try to reduce my error. If I don't manage to do that, I say, okay, stay more in the situation where you've been before. Just make smaller updates and see if I can reduce the error. And I kind of continue with that. And then if I was able to reduce the error with my updates, I try to again say, okay, go closer to the solution, to the system I want to solve, and stay less in the current setup, and then until I converge. Okay, so as you can see here, the idea of moving from this postgraph to a graph as landmarks is actually not a dramatically big step. So I have different error functions. I have new nodes, so to say, in my graph, which have new error functions. And the only problem this really introduces is, depending on the rank of those constraints, I can end up in situations where my H matrix doesn't have full rank, and then I can't solve it with the standard approach which we discussed last week. So I have to go for a different approach, and one way to do this is to use the Levenberg-Marquardt algorithm to do the optimization. And that's what we did so far. I'm sorry, these two things don't matter anymore. I just split up this chapter into the first part, which will be add-on, before in one presentation. So these two summary items are the one we discussed in the first lecture today. I just forgot to remove it from the summary slides. So what you ended up with here is you should know how to deal with landmarks now, and you should know how to deal with situations where you have a system which has not full rank, which especially happens, for example, in visual applications. So if you use just cameras to do that, then you easily run into those situations. You need to take these kind of approaches, otherwise you will not come up with an appropriate solution. Are there any questions? Okay, so thank you very much, and see you next week.